Drag a sled with a rope slung over your shoulder. The rope pulls upward and forward, but the sled moves only forward, so only part of your pull does any work. Physics has one operation that extracts exactly that part, the scalar product. It takes two vectors and returns a single number that measures how much they cooperate. In this video, we define it, compute it in components, and use it to rewrite kinetic energy and work. Then let it dissect a block sliding down a rough incline. Start with two vectors, call them A and B. Any two non-collinear vectors define a plane, so draw both from a common origin and let theta be the angle between them. Theta runs from 0 to pi. The scalar product, written A dot B, is defined as the magnitude of A times the magnitude of B times the cosine of theta. Whatever the two vectors are, the output is a single scalar number, no direction attached. Its sign tracks the cosine. When theta is less than pi over 2, the cosine is positive, and so is the product. When theta equals pi over 2, the product is 0. When theta is greater than pi over 2, the cosine turns negative, and the scalar product comes out negative. The definition runs both ways. Given the scalar product and the two magnitudes, solve for the angle. Theta equals the inverse cosine of A dot B, divided by the magnitude of A times the magnitude of B. The dot product becomes an angle measuring tool. Next, dot a vector with itself. The angle between a vector and itself is 0, and the cosine of 0 is 1. So A dot A is just the magnitude squared. Take the square root. The magnitude of any vector equals the scalar product of the vector with itself, raised to the 1/2 power. Remember this identity. It is exactly the doorway through which kinetic energy will meet the dot product. The scalar product also has a geometric reading. Group the definition as a cosine theta times b. The factor, a cosine theta, is the projection of vector A onto the direction of B, the shadow that A casts along B's line. So the scalar product is the projected length of A along B times the full length of B. Group it the other way as A times B cosine theta, and the rows swap. Now B cosine theta is the projection of vector B onto the direction of A. Both readings give the same number, one vector's length times the other vector's shadow along it. This picture makes the zero case obvious. When the two vectors are perpendicular, the angle is pi over 2 and the shadow shrinks to a point. No projection, no product. Perpendicular vectors have a scalar product of 0, no matter how long either one is. To compute dot products in coordinates, start with the Cartesian unit vectors, I hat, j hat, and k hat, each of length 1. Dot a unit vector with itself and the angle is 0, cosine equal to 1, so I hat dot I hat equals 1, and the same for j hat and the k hat. Dot two different unit vectors and they are perpendicular, so the product is 0. Thus, I hat dot j hat dot k hat, and I hat dot k hat all vanish. Matched pairs give 1, mixed pairs give 0. Those two facts are the complete multiplication table for the coordinate dot product. Now take two general vectors in components. Vector A equals A sub x I hat plus A sub y j hat plus A sub z k hat, and the vector B is written the same way with its own 3 components. Dot them and distribute the product across every pair of terms, 9 terms in all. Each mixed term carries a unit vector factor, like I hat dot j hat, which is 0, so 6 of the 9 terms die immediately. Each matched term carries a factor of 1 and survives. What remains is the component formula. A dot B equals A sub x times B sub x plus A sub y times B sub y plus A sub z times B sub z. No angle in sight. Multiply matching components and add them up, and the result automatically equals magnitude times the cosine of the angle. Because the component formula is a plain sum of products, it differentiates by the ordinary product rule. Take the time derivative of A dot B. In components, the time derivative of a sub x times b sub x plus a sub y times b sub y plus a sub z times b sub z. The product rule hits each term twice. The derivative of the a component times the b component plus the a component times the derivative of the b component. Now regroup all 6 pieces. The terms that differentiate the components of A assemble into the vector dA by dt dot b. The terms that differentiate the components of B assemble into A dot dB by dt. So the time derivative of A dot B equals dA by dt dot b plus A dot dB by dt. The product rule survives in vector form. One special case matters most. Set B equal to A. Then A dot A is the magnitude of A squared, and the product rule gives its time derivative dA by dt dot A plus A dot dA by dt, but the scalar product is symmetric. The order of the 2 vectors does not matter, so those 2 terms are equal. The time derivative of A squared is twice, dA by dt dot A. Tuck this identity away. Applied to velocity, it links the rate of change of speed squared to the acceleration. Now put velocity into this machinery. For an object moving in 3 dimensions, the velocity is v sub x I hat plus v sub y j hat plus v sub z k hat. The magnitude of a vector is the square root of its dot product with itself, so the speed squared is exactly v dot v. In components, v sub x squared plus v sub y squared plus v sub z squared. Kinetic energy is 1/2 the mass times the speed squared. So kinetic energy equals 1/2 m times v dot v, which is 1/2 m times the sum of the 3 squared components. Written this way, kinetic energy is a statement about the velocity vector itself, valid in any direction and in any coordinate system. Here is the payoff. Work. When a constant force acts on a body moving along the x-axis, only the force component along the motion does the work. W equals F sub x times delta x. Now pull a body along a horizontal surface with a force that makes an angle beta with the positive x direction. The force is F sub x I hat plus F sub y j hat. The displacement of the point of application lies along the x-axis, delta x times I hat, and the delta x is a component, so it can be greater than, equal to, or less than 0. Dot the force with the displacement. The j hat part of the force meets no j hat displacement and contributes nothing. The I hat part multiply to give F sub x delta x. That is precisely the work. So work is the scalar product of force and displacement. W equals F dot delta x. And since F sub s equals F cosine beta, where beta can range from negative pi to pi, the work is also F cosine beta times delta x, the magnitude of the force times the cosine of its angle to the motion times the displacement component. Time to let the dot product do real work. Here is the problem. An object of mass 4 kilograms starts from rest and slides down an inclined plane of length 3 meters. The plane is inclined at 30 degrees to the ground, and the coefficient of kinetic friction is 0.2. 3 questions. What work does each of the 3 forces acting on the object do while it slides down? Is each of those works positive or negative, and what is the sum of all 3? First, set up coordinates on the picture. Put the origin at the top of the incline. Point the positive x direction down the slope and the positive y direction perpendicular to the surface towards the upper right. With this choice, the motion is one-dimensional. The object slides 3 meters along the surface, so its displacement is delta r equals Li hat. The length L of the plane, straight down the slope. 3 forces act on the object, and the free body diagram shows them. The gravitational force, magnitude mg, points straight down, toward the ground, not along the slope. The normal force N acts perpendicular to the inclined surface, and the kinetic friction force points up the slope, opposing the sliding with magnitude mu sub k times n. Before computing any work, we need n. The object never leaves the surface, so its acceleration perpendicular to the slope is 0. Newton's second law along j hat reads n minus mg cosine theta equals 0. So n equals mg cosine theta, and the friction has magnitude mu sub k mg cosine theta. Now decompose the three forces in the tilted coordinates. Gravity has a component mg sin theta pointing down the slope, and mg cosine theta pressing into it. The vector is mg sin theta I hat minus mg cosine theta j hat. Friction is pure I hat and negative, minus mu sub k mg cosine theta. I hat. The normal force is pure j hat, mg cosine theta, j hat. Take the dot products, one force at a time. The normal force is pure j hat, dotted with a displacement that is pure I hat. J hat dot I hat is 0, so the normal force does 0 work. Perpendicular to the motion means no work. The dot product says it instantly. Friction minus mu sub k mg cosine theta. I hat dotted with li hat. The I hat terms match, giving minus mu sub k mg l cosine theta. Substitute the numbers. 0.2 times 4 kilograms times 9.8 meters per second squared times 3 meters times the cosine of 30 degrees, negative 20.4 joules. Negative as friction's work must be. Friction points opposite the displacement. The angle between them is pi, and the cosine of pi is negative 1. Gravity, the j hat component dies against the I hat displacement, and the I hat component gives mgl sine theta. Substitute 4 kilograms times 9.8 times 3 meters times the sine of 30 degrees, which is 1/2, and gravity's work is 58.8 joules. Positive, the downhill part of gravity pushes along the motion. Finally, sum the three. 0 minus 20.4 plus 58.8, 38.4 joules in total. Positive. In symbols, the total is mgl times sine theta minus mu sub k cosine theta. The dot product sorted the three forces at a glance. The perpendicular force gave 0, the opposing force gave negative, the aligned component gave positive. And the positive total is the energy that shows up as the object's speed at the bottom. One operation carried this entire video. The scalar product takes two vectors and returns one number, magnitude times magnitude, times the cosine of the angle between them, or equivalently matching components multiplied and summed. It measures alignment positive when vectors cooperate, 0 when they are perpendicular, negative when they oppose. Dot velocity with itself and you get speed squared, the heart of kinetic energy. Dot force with displacement and you get work, sign included with no extra bookkeeping. Whenever a problem asks how much of one vector acts along another, the scalar product is the answer. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.